The quantum harmonic oscillator is one of the most fundamental quantum systems you'll encounter in your quantum mechanics course. And for a reason, in the one-dimensional case, it's the simplest system to solve. And it starts like this. So suppose you have a one-dimensional space along the x direction, and your box extends from the origin to, let's say it's a box of length L. Your potential for, in case of an infinite potential well, you have on this side potential of infinity, and on that side a potential of also plus infinity on either side. And in this region, the potential is 0, and your particle supposedly is residing within these two boundaries. Mathematically, we can write the potential as follows. It's v of x is going to be 0 for x is in between 0 and L, so it's within the box, and it's infinite elsewhere. Now, in order to, in quantum mechanics, our goal is to determine the wave function psi as a function of x, because the probability, because psi contains all of the information that we need to describe the particle. For example, if we want to position or to calculate the momentum, all the information are within psi. And for example, the probability of finding the particle in a position x is proportional to the squared magnitude of psi. And in order to calculate psi of x, the energy eigenstates for, let's say, a particle in a box, we will have to use the Schrödinger equation, and specifically the time-independent Schrödinger equation, where if you apply the Hamiltonian on psi, it gives you the energy multiplied, the energy eigenvalue multiplied by your wave function psi, where psi is an energy eigenstate. So our goal here is to find what is psi and what is the energies. What are the energies, if we may, from this differential equation. So typically in a classical particle, the energy will equal the kinetic and the potential energy, and we can rewrite that as p squared over 2m, which is your typical half mv squared, but remember that the momentum is equal to the mass of the particle multiplied by its velocity, so you can rewrite the kinetic energy as follows, and the potential, which is some random function that you can choose as a function of position. In our case here, we know the potential, it's a piecewise potential, so it's infinity outside of the box and it's 0 inside of the box. So we have to solve the Schrödinger equation in 3 different regions. So we have to solve it in region 1, in region 2, inside the box, and region 3 outside the box again. And so our Hamiltonian, from this classical description, we can define our Hamiltonian accordingly to be the momentum operator squared divided by 2m, so that's the kinetic energy term, plus the potential term. And we can solve the Schrödinger equation to begin with, 1 and 3. So in regions 1 and 3, because they're similar, the potential is infinite, right? So the potential is equal to infinity. And we can observe the Schrödinger equation in this case. So the Hamiltonian multiplied by psi must equal some energy eigenstate multiplied by psi. And if we expand the Hamiltonian in terms of this equation that we wrote earlier, so it's p squared over 2m plus some potential multiplied by psi is equal to the energy eigenvalue multiplied by psi. So any particle will have its energy be finite. So the energy must equal a finite value. In our case, in regions 1 and 3, the potential is infinite. So, and the kinetic energy is also finite. So this is finite. This is also finite, but this is infinite. Goes to infinity. So the only way this equation will make any kind of sense is that if psi is equal to 0. That's the only way to make sense of the equation. So psi in regions 1 and 2 must equal 0. So the particle cannot exist in these two regions. Now we have the solution in region 2, where the potential is equal to 0. Then we can substitute in the equation p squared over 2m plus 0 applied on psi will give us the energy eigenvalue multiplied by psi. And we note that the momentum operator is equal to minus I h bar d by dx. Substituting that back into the equation, we get that minus h bar squared divided by 2m d squared by dx squared of psi is equal to E psi. And so the equation becomes d squared by dx squared psi, d squared by dx squared psi is equal to minus 2me over h bar squared psi. Where now we're going to choose this, define it as some variable k squared, such that k squared is equal to 2me over h bar squared. Now we are certain that the energy in this case must be positive, since the energy of the particle is only its kinetic energy. There's no potential term, so E is positive, so it makes sense to define it k squared as 2me divided by h bar squared. And so the differential equation becomes d squared x squared of psi is equal to minus k squared psi. And so this is a well-known differential equation, and you can write the solutions as complex exponentials. So taking the second derivative of psi with respect to x is equivalent to, it gives you psi back, but multiplied by k squared and with a negative sign, so it changes the sign. There are two kinds of functions that do that. It's either a complex exponential or a sine and a cosine. In this case, it's better to expand psi as a linear combination of sines and cosines. So we can write it as follows: kx plus p cosine kx. So this is basically our eigenstate solution, but we still have the boundary conditions to worry about, which says that psi at 0 must equal 0. Remember, from the continuity, because the particle cannot exist in this region of infinite potential. And psi of L must also equal to 0. Hence, from these two equations, the first one, psi of 0, will equal a sine of 0 plus b cosine of 0 must equal 0. The sine of 0 is equal to 0, so this term disappears. The cosine of 0 is equal to 1, so this leaves that b must equal to 0. The second equation tells us that psi must also vanish at x equal to L, so a sine kl must equal to 0. Now in this case we have two solutions. So you either have a is equal to 0, which is a trivial solution, because if a is equal to 0 and b is equal to 0, then psi of x will always be equal to 0, which is obviously a solution to this differential equation. So it's a trivial solution. A more interesting solution appears when we take sine kl to equal 0, which means that KL must be a multiple of pi. That's the only time, an integer multiple of pi, which makes the sign vanish at this position, meaning that K is n pi over L, where n belongs to the integers. So n can be 0, plus or minus 1, plus or minus 2. But we're going to discuss the value of 0 and the negative values as well, just until in just a second. So psi n of x will look something like this. So it's a sine n pi over L x. Now, if n is equal to 0, then you have psi n of x is 0 for all x. So we're back to that trivial solution case, so we don't want n cannot be 0. Okay, so what about the negative values? Well, you always know that when you have a sine function and you take sine of minus x, it's equal to minus sine of x, because it's an odd function. You can take the minus outside of the function and it's exactly the same. But we know that that the probability of x, of finding the particle at a position x, is proportional to the magnitude or the modulus squared of psi, so that whether you have psi or some constant multiple of psi, you will always have the same physics, meaning that the negative values for n are redundant, so we only need the values 1, 2, 3, and so on. So only positive definite integers are allowed, and essentially these are our wave functions. Psi n of x equals a sine n pi over L x. Okay, and we've already, so the wave functions are integer multiples, so they're kind of quantized, but also we have that k, we have seen that k is equal to an integer multiple of pi over L. So remember that k equals n pi over L, but also k squared equal 2m e over h bar squared, which means that e sub m will equal h bar squared over 2m k squared, but k is equal to n pi over L squared. So that's our solution for the energy eigenvalues to the corresponding eigenstates. And we can notice that the energies are quantized. An interesting thing occurs, however, when you try to solve the exact same problem we had earlier, but in a symmetric potential well. So suppose that you have the same one-dimensional particle, but this time, instead of your well going from the origin to L, it goes from minus L over 2 to L over 2. And again, here you have the forbidden region of having infinite potential on either side and 0 in the middle. So within the box, we can rewrite our potential function as follows. So v of x is equal to 0 for x, this time going from minus L over 2 to L over 2, and it's infinite elsewhere. So now we can again divide the problem into 3 regions: region 1, region 2, which is within the box, and 3 outside the box. In regions 1 and 3, for the same reasons discussed earlier, the psi must equal 0 because the particle must have finite energy, and in this region the potential is infinite, so the energy will be infinite if it were to exist within that region. So we limit our study to to region 2, which is within the box. And so following the similar derivation we did earlier within the asymmetric potential well, which went from 0 to L, we had d squared psi by dx squared is equal to minus k squared psi, where, if you remember from earlier, k squared equals 2m e divided by h bar squared. So the derivation up until this point will be exactly similar to the one we did earlier. The solution obviously will also be a sum of sines and cosines, a sine kx plus b cosine kx. But now the boundary conditions, are slightly different. So you have the psi must vanish for minus L over 2, it should be 0, and psi must also vanish at L over 2. So we'll have, substituting these two equations up here, we will get a sine, so this is the first equation, and this is the second one. We get, in the first one, we'll get a sine k minus L over 2 plus b cosine k minus L over 2 must equal to 0. But remember, the sine is an odd function and the cosine is an even function, so we'll get minus a sine k L over 2 plus b cosine k L over 2 must equal 0. That's from the first equation. And the second equation is a little bit more straightforward. We just substitute L over 2, so we get a sine k L over 2 plus b cosine k L over 2 is equal to 0. That's our second equation. And intuitively, to solve, we need to solve for a and b, so we can just sum these two equations. Notice that these two terms will cancel each other, and we'll get that b cosine 2b cosine k L over 2 must equal 0. And we have two cases. So the first case is when b is equal to 0. Okay, so when b is equal to 0, you'll have to have a sine kl over 2 is equal to 0. And you'll have that kl over 2 is equal to some multiple of pi, so it must be n pi. So k will equal 2n pi over L. So already we can see that k is different from the one that we had from the previous example, which had k was equal to n pi over L. Now it's kind of different. It has a factor of 2. But no worries, we'll continue with our derivation. So we'll get that psi n of x, in this case, will be some constant, normalization constant will be, and sine 2n pi over L multiplied by x. And you'll have that the energy, remember that we had k squared is equal to 2me divided by h bar squared, which means that E, the energy, E sub n, will be equal to h bar squared over 2m multiplied by k squared, which in our case is 2n pi over L squared. So these are our first solutions to the equation. And so you get these two solutions. Now, what if the cosine instead, so you have the second case of having cosine KL over 2 is equal to 0. So cosine of KL over 2 is equal to 0. Then KL over 2 must be an odd multiple of pi over 2, because remember the cosine is 0 for if it's a multiple of, if it's a 90 degrees or or 270 degrees and so on. So it must be an odd multiple of pi over 2. So k in this case will be 2n plus 1 pi divided by L. So the energy eigenstates will be En is equal to h bar squared over 2m, 2n plus 1 multiplied by pi divided by L, all of it squared. And already you can see between the two energy eigenstates, you'd think that these two expressions are different. So for this n value, you'll have an energy, and for the same n value there, you'll have a different energy. So what's the difference? We just shifted the coordinate system by and made the problem symmetric, and somehow we have two energy values that arise out of nowhere, it seems. But we'll get to the punchline in a second. So now we have psi n, since that cosine KL over 2 is equal to 0, that means the minus a sine KL over 2 must also, or a sine KL over 2 must also equal to 0. So because from this equation, b is different from 0, but cosine KL over 2 is equal to 0, then a sine KL over 2 must also equal to 0. So a sine KL over 2 must also equal to 0. But if you substitute k for the value that we just found, so it's going to be a sine 2n plus 1, and you have 2n plus 1 pi over L multiplied by L over 2 must equal to 0. And you'll have a sine, if you remove the two L's, you'll have 2n plus 1 pi divided by 2 must equal to 0. Now, an odd multiple of pi over 2 will always yield you some sort of, it will always be some multiple of 90 degrees. So the sign will always be 1, which means that you have to have a equal to 0 for this solution. And so you get psi n of x in this case will equal b cosine k. K in this case is 2n plus 1. So it's going to be 2n plus 1 pi over L multiplied by x. And your energy eigenstates are as follows. Now, I've rewritten these two solutions side by side so we can compare to what we had originally. So in the case where the potential was between 0 and L, you had psi n of x is equal to some multiplicative constant multiplied by a sine function and pi over L x. And your energy eigenstates were h bar squared by 2m multiplied by n pi over L squared. So this was the previous solution. But now what we've done essentially is we've moved our coordinate system to the left by half a unit. So now your box is symmetric with respect to the origin. And for some reason, you have two different wave functions that describe your system, and you have what appears to be two different energy eigenstate values. So did we just create energies out of thin air? Is physics like that? So if someone defines a coordinate system that is slightly different than yours by linear transformation, will measure different energies? No, it's not really the case. Well, the even though the eigen functions appear to be different, the probabilities remain the same. That's one. Two, the energies appear to be different, but they really aren't, because if you examine here, it's 2 times n, and here you have 2n plus 1 multiplied by pi. 2n will always equal an even number, no matter what you do. For all n, so n is equal to 1, n is equal to 2, 3, you'll always get an even number, and 2n plus 1 will give you an odd number. So essentially shifting your system by half a unit to the left didn't create energy eigenstates. They are all encoded within our previous solution, but they are separated in a way that the even functions have their own eigenstate and energies, and the odd functions have their own eigenstates and energies, but together combined, they describe the system exactly the same way and exactly as well as the previous system that we have calculated. Something else that we didn't discuss was within our first solution was this constant A. We didn't mention uh, what its value was, we just left it as is, but this one is just a normalization constant that can be determined by the fact that we would like our eigenstates to be properly normalized so that the probability x, so if you integrate the probability over all possible values, it must equal 1. And since the probability of x equals psi squared, or is proportional to the modulus of psi squared, then we would like our wave functions psi sub n of x, the modulus squared of them, to equal 1. Then, and this is integrated over all space. This is integrated over all space, and so that in our case we have 3 regions. So you'll integrate. So we're integrating from minus infinity to plus infinity. Psi squared dx must equal to 1, and we must split our integral into the 3 different regions that we had. So 1, 2, and 3. So you'll have from minus infinity till 0 psi sub 1 psi dx plus psi squared dx plus the integral from 0 to L. In the first case where we had the box extend from 0 to L, psi squared dx psi sub n squared dx plus the integral from L to plus infinity psi squared dx. But remember, in these regions, in region from minus infinity to 0, your psi was 0, and from L to plus infinity it was 0. This must equal 1. So the integral from 0 to L, psi sub n in this region, it's equal to a sine n pi by L over x. So you'll have 0 L a squared sine squared n pi over L x dx must equal to 1. A squared is a constant, so it gets out of the integral. So we're left with the integral of sine squared n pi over L x dx must equal to 1. Note that sine squared of theta equals 1 minus cosine of 2 theta divided by 2. So what do you get by substituting that here is that the integral from 0 to L of half minus half cosine 2n pi over L x dx must equal to 1. Now, the integral of a cosine over an entire period is 0 because the average value of the cosine is 0. So you're left with the integral of a half multiplied by the x, so you'll get a squared. L over 2 must equal to 1, which implies that a is equal to the square root of 2 over L. And our wave function becomes our properly normalized wave function will be in this form.